Hi, and welcome back. This week, we'll talk about anaerobic digestion. Sometimes this is also called biomethanation, or sometimes just called biogas treatment. I will probably often use the abbreviation AD for anaerobic digestion. For this module, I'm using this book published by Sundek as a main resource. It's called Anaerobic Digestion of Biowaste in Developing Countries. You can download this book on our website, and it's free of charge. You will probably remember that in the past few modules, we have covered composting as one option for biowaste treatment. As you now know, composting is a process of controlled aerobic degradation. That means with air or with oxygen. You see this clearly here, this composting heap, which has a passive aerating tunnel in the center. In this module, we'll talk about anaerobic digestion, which is the collection of processes where microorganisms break down biodegradable matter in the absence of oxygen. This is very common to many natural environments, such as swamps or stomachs of ruminants, cows. So why is this interesting for waste management? Because in anaerobic digestion, microorganisms produce biogas. That's a mixture of methane and carbon dioxide. Methane is really what is interesting because it's flammable and can be used as an energy source. In addition, what we also get is a nutrient digestate. Anaerobic digestion is becoming very, very popular for waste management. In Europe, many units are being built and operated, and even in developing countries, it's becoming very interesting, especially from the point of view of renewable energy resource. What we are especially interested in is using this process in an engineered way with controlled design, for instance, in an airproof reactor, in digester, to produce biogas and digestate, as you can see on this picture. So, what are the key benefits of anaerobic digestion? Of course, we're producing renewable energy, and that means we're reducing our dependency on fossil fuels. We're also reducing greenhouse gases. AD is pretty good because it doesn't need much space. We can actually build the reactors underground. Of course, it also reduces solid waste volumes and thus avoids disposal costs. And it reduces pollution from waste and pollution from fossil fuels. Finally, of course, we can recover value from waste in the gas and the nutrients. There are also a few drawbacks of AD, especially when comparing to composting. The process of AD is more sensitive. It's slower and it's less energy intense. In fact, the energy is contained in the methane. But that means that there is also no heat generation, and that has implications for hygienization. AD is also technically more complex, and therefore also needs higher levels of skills and investment. Now let's look at the biochemical processes. Anaerobic digestion happens in 4 steps, although these processes happen partly simultaneously. The first step is hydrolysis. It is the slowest of the 4 degradation steps. Bacteria transform complex organic materials into liquefied monomers and polymers. The second step is acidogenesis. That's where sugars and amino acids are converted. The third step is acetogenesis. That is where the substances are then transformed into hydrogen, carbon dioxide, and acetic acid. Finally, the last 4th step is methogenesis, where the methogenic bacteria convert hydrogen and acetic acid into methane gas and carbon dioxide. Typically, the gas mixture will also contain hydrogen sulfide. That's the stuff that smells of rotten eggs, but also nitrogen, oxygen, and hydrogen. In volume percent, methane amounts to roughly about 60%, while CO2 is around 40%. Hydrogen sulfide is usually lower than 2%. Now let us look at the parameters and operational conditions and how these influence the anaerobic digestion process. Let's start with the feedstock, also called the raw material or input material. We can distinguish between the solid content and the water content. The dry matter is also what we call total solids. Now, some of these total solids will be biodegradable and some won't. In this context is, of course, the biodegradable organic fraction that is relevant, and this we call volatile solids. Levels of total solids and volatile solids in waste differs depending on the type of waste. In this table, you can see some examples regarding total solids and volatile solids of different waste feedstocks. Depending on the type of waste, you can also expect different amounts of methane yield, as shown in this table. Interestingly, lignin, one of the main wood constituents, doesn't degrade under anaerobic condition. So this anaerobic digestion is not really suited for treating yard waste or woody waste. You can see this here in the last row, where methane yield of lignin-rich organic waste is quite low. An important parameter in AD is the organic loading rate, OLR. This parameter quantifies the substrate quantity per reactor volume and time. The unit is kilograms volatile solids per cubic meter and day. A good daily loading rate for unstirred reactors is 2 or below. With a stirred reactor, this can be higher. You can increase this up to a loading rate of 8. The pH range for anaerobic digestion is between 6.5 and 7.5, so actually quite neutral. However, in the acidic phases, the pH is rather lower, whereas in the methogenic phase, it is somewhat higher. Now, if the loading rate is too high, acidogenic bacteria will cause acidification of the reactor. Methanogenic bacteria are rather more sensitive to these conditions and will thus be inhibited. To react to this, the loading rate should be reduced, or one can also add lime or sodium hydroxide to increase the pH level. Another factor influencing the AD process is temperature. Temperatures below 15 degrees Celsius are not ideal, as then the organisms really slow down their activity. Underground construction or insulation can buffer this variation of temperature. But the anaerobic process is most comfortable in 2 temperature zones. The mesophilic temperature zone between 30 and 40, and the thermophilic temperature zone between 45 and 60. Operation in the mesophilic range is more stable and can tolerate greater changes in environmental parameters and consumes less energy. However, mesophilic organisms are slower in degrading, and so you need to give them more time. Thermophilic organisms, however, are faster, but the system is more sensitive to changes. A further parameter that influences the process is hydraulic retention time. That is the amount of time that the material stays in the reactor. Ideal is a time between 10 and 40 days. The lower value is rather for higher temperature in the thermophilic range, because the process is quicker. Now here we're confronted with an optimization process. If for a given input the reactor volume is small, then the retention time is low, which means we will get little biogas yield, as there is little time for the process. If the reactor volume is large, then retention time increases and we get more yield, but at the cost of having a large reactor, meaning more space needed and higher investment costs. Another parameter is the CN ratio. We've already heard about this in the composting module. Ideal is a value between 16 and 25. A higher value means limited supply of nitrogen. That means food for the bacteria, and therefore less gas production. A lower CN ratio can cause ammonia accumulation, which then inhibits the anaerobic process. The last parameter we'll look is about particle size of the input material. Here, small is beautiful. Particle sizes below 5 centimeters are ideal. What that does, it increases the surface area of the material and allows the microorganisms to faster degrade the material. For operation, that means that usually we chop up through a shredder our input material to make small particles. So, let me summarize what we covered in this module. We looked at benefits and drawbacks. We looked at the 4 stages of the biochemical process, and then we looked at different operational parameters: input material, organic loading rate, pH, temperature, hydraulic retention time, CN ratio, and finally particle size. In the next module, we will look at different types of reactors and how to operate them. So, stay with me for the next module.